And now we are going to see an example to produce 200 million pounds per year in a CSTR. It is desired to produce 200 million pounds per year of ethylene glycol. The reactor is to be operated at temperature constant. A 1 mole pound per cubic feet solution of ethylene oxide in water is fed to the reactor, together with an equal volumetric solution of water containing 0.9 weight of the catalyst, which is sulfuric acid. The reaction rate constant is 0.311, which we evaluated in the example 4.1. The conversion, if 80% conversion is to be achieved, determine the necessary volume of the CSTR. If we have 800 gallons reactors and we are arranging in parallel, which is the conversion, and if we have those 800 gallons reactors and we are arranging in series, which is the conversion. So here we have the two reactants, ethylene oxide and water, are going into the reactor, and we are getting as a product ethylene glycol. The specified ethylene glycol production rate in mole pounds per minute is going to be, they want us to produce 200 million pounds per year. So those 200 million pounds per year, we will put it in mole pounds per minute with all this conversion of unit of years to days, and then to hours, and then to minutes, and the pounds going from pounds to mole pound by using that 1 mole pound is equal to 62 pounds for the ethylene glycol. So FC is equal to 6.137 mole pounds per minute. So here the demand of the market is telling us which is the molar flow rate that we need at the exit of the reactor, and from here, from FC equal FA0 times X, we will get how much do we need to put in the reactor of the reactant. So we find the required molar flow rate of ethylene oxide to be FA0 equal FC divided by X. So is this going to be 6.137 divided by 0.8, which is 7.67 mole pounds per minute of ethylene oxide. Now, we are going to the algorithm. The first thing that we need in the algorithm is the design equation. And the design equation is B equal FA0 times X divided by minus RA. This is coming from the mole balance. And then we have the rate law. The rate law, they tell us that is a first order, so minus RA equal to K's, the concentration of A to the first power. From stoichiometry, we know that the concentration of A is equal to CA0 times 1 minus X, because the volumetric flow rate is constant. And if we combine these three, we will come that the volume of the reactor is V0 times X divided by K times 1 minus X. And now we are going to evaluate. The entering volumetric flow rate of A is CH0 is 1 mole pound per cubic feet. And so if that's the concentration, then the volumetric flow rate of A0, BA0 is going to be FA0 divided by the concentration CH0. This is going to be 7.67 cubic feet per minute, and is entering the same volumetric flow rate of water. We will have that the volumetric flow rate of water is to 7.67 cubic feet per minute. So from here, we will get that the molar flow rate of water is equal to 7.67 cubic feet per minute times the density of the water times the conversion of pounds to mole pound. We will have then that FB0 is equal to 26.6 mole pounds per minute. So the total entering volumetric flow, which is the sum of the two, is going to be 15.34 cubic feet per minute. And if we have that K is equal to 0.311 minus to the minus 1, we will substitute those values into the equation for the volume, which is V0 times X divided by K times 1 minus X, and we will have that the volume is equal to 5.6 cubic meters. Now, if we put these two CSTR in parallel, and the two have 800 gallons of volume each one, and we put them in parallel, so the volumetric flow rate is going to be 7.67 because the total volumetric flow rate is going to be divided by 2. And the conversion achieved can be calculated like the equation V0 times K is equal to tau times K equal to X divided by 1 minus X. From here, the conversion is tau K divided by 1 plus tau K, and tau is the volume, which are 100 gallons, and we multiply by the factor to go from gallon to cubic feet, and we divide in the volumetric flow rate, which is 7.67 cubic feet per minute, so we will have that tau is 13.94 minutes. From here, the damn core number is 13.94 times 0.311. That will give us 43.4. And here, the conversion is going to be the damn core number divided by 1 plus the damn core number. It's going to be 4.34 divided by 5.34 is equal to 0.81. And from here, we see that if we put the two reactors in parallel, the conversion at the end of these reactors is going to be 0.81. But what about if we put the two reactors of 800 gallons in series? Well, if we put them in series, S1, the conversion from the first reactor is going to be tau 1K divided by 1 plus tau 1K, and tau 1 is going to be the volume, the 800, divided by the volumetric flow rate, but now the volumetric flow rate is going to be 15.3.4 because all is going to one reactor. We are not dividing the volumetric flow rate in two. So tau 1 is going to be 6.97 minutes. From here, the damn core number, DA1, is going to be 2.167, and X1 is going to be the damn core number divided by 1 plus the damn core number is going to be 2.167 divided by 3.167 equal to 0.684. And to calculate the conversion of the second reactor, we must recall that all the reactors have the same volume, all of them have the same volumetric flow rate, so as a consequence, they will have tau equal to. So a mole balance in the second reactor is in minus out plus generation equals 0. In is coming FA1, out is going FA2, and is generated air, the rate A2 times the volume. So the volume is going to be FA0 times X2 minus X1 divided by the rate. And the rate, because it's a first order, is KCA at the second reactor elevated to the first power, which is going to be KCA0 times 1 minus X2, and the volume of the reactor is going to be V0 divided by K times X2 minus X1 divided by 1 minus X2. So if we resolve for X2, we will have that X2 is going to be 0.9. So if we put the two reactors in series, the conversion is going to be higher than if we put the two reactors in parallel. So 200 million pounds of ethylene glycol per year can be produced using two 800 gallons reactor in series.